Hey, John here. So last time we talked a little bit about the relationship between the assembly language statements, the way we encode them, this usage template column here, and what the machine will do when it encounters one of these instructions, all right? I added links to these fields here, the PC relative fields, because the relationship between what you put in the source code when you write one of these instructions and what gets encoded in the instruction and used over here is not necessarily a one-to-one thing, all right? Now, I've also added the usage template column from the previous page to this page here on instruction set encoding, basically for the same reason. I want to express the relationship between the parameters in these instructions and how they're encoded over here. Now, the way these links work is if you click on U-type, it discusses the encoding of all U-type instructions. You can click on Louis here, and it'll tell you specifically how the Louis instruction works. And you can click on one of the operands over here, like this IMM field, and it'll discuss the relationship between what you put in your source code and your assembly instruction and how it gets encoded when it gets put into the instruction that's stored in memory. And that is the subject of today's discussion. Because in order to have a conversation about the relationship between the organization of a machine and the architecture of the machine, it would be nice to be able to discuss it in terms of the assembly language rather than the machine language, all right? So let's connect these two together so we can speak in terms of just these instructions, all right? So as I discussed before, this column here has the opcode in it. This column over here has what we call function 3. The immediate values and the register numbers are stored in various fields in the different types of instructions. The func7 field over here is used in some of these instructions to differentiate between subtracting and adding and arithmetic shifting versus logic shifting and so on, right? So let's go through these by group. There's U-type, J-type, I-type, B-type, and so on. The various types refer to how these fields are organized in the instructions. Look at all the I types have the same exact fields in the same order in the same places, all right? So you have the various load. These are load instructions that load values out of memory and into registers. They're all I-type instructions. Why? Because they require a destination register and a source register and an immediate value. Okay, there's also I-types down here that have to do with ALU operations. They too have a destination, source register, and an immediate value. But look between the I-types up here and the I-types down here. They're not expressed the same way in your assembly language source code. In spite of the fact that they're member of the same type, we express them differently. And that, if you think about it for a minute, it might make some sense, right? Add immediate means take this number that's stored in the instruction itself and then add it to the contents of whatever is stored currently in our register RS1 and store the result in the destination register, okay? And that is how we express that. In a load instruction, what we're really using here is a base displaced addressing mode, okay? So what I would like to be able to do is say like load register 4, if I wanted to, x4, right? With the value in memory that's maybe, I'd set IMM here, maybe it's 8 bytes displaced off of the contents of, register 4. If you're familiar with mainframe assembler, this is what we would call a DB addressing mode, a base displaced addressing mode, right? We talked about that when we looked at the 68K as well. Now, the RISC-V does not have as many addressing modes as the 68K does. It has immediate and it has base displaced, and that's it. It doesn't have the multiplication scaling factors and things like that. It doesn't have all that fancy stuff. It's just an absolute minimalist machine, which is the main reason I'm focusing on it in this video. Since the RISC-V only has about 40 instructions or so, there's a lot less that we have to talk about. But at the same time, we have an actual and real machine that can execute real programs. So now let's start with what is arguably perhaps one of the easiest set of instructions to deal with. All the R-type instructions are in this one grouping down here. They all have the exact same opcode. Notice what's happening, by the way, with these opcodes. Even though we have a couple of different kinds of R-type instructions, we have these shift ones, we have these immediate operand instructions that perform ALU operations, and we have the load instructions in here, okay? They're in these different groups because they have different opcodes. Look what's going on here. This opcode is a 3 in binary, right, for all the loads. Down here, all these ALU immediate instructions have in hex a 1-3, right? Remember, these slugs show you where the hex boundaries are, so you don't have to count all these bits in your head. I added these for myself. First time I was trying to explain how to do this, I found myself counting them out. It drove me nuts. I put these in here for myself. I know they're useful. I hope you find them useful as well. Anyway, the point is, all of these I-type instructions are literally encoded identically, but they have different manners of expression in assembler. I mentioned that already. And the manner of expressing the assembly language, is my point of this current digression, has to do with the way the opcodes are set up. Look what's going on here. Each of these have the same opcode, and therefore they're encoded like this. Now, the shift amount ones are technically the same. If you look at the official RISC-V documentation, these are lumped together in one group. I separated them because the shift amount field is used differently for the shift instructions than it is for the ALU ones up here. And that is that specifically on a 32-bit machine, the shift amount is only 5 bits in size because you can only shift the thing up to 31 bits. If you shift it 32 bits, in theory, the value would be 0. Okay? So there's no reason to shift it that far. All right? So it ignores, or at least declares as illegal, setting any of the other bits over here, except for in the case of this one column. All right? Remember, we talked about this last time, the arithmetic versus logical shifting. And that is the reason I put these into 2 separate groups. On the other hand, they literally are the same because they all have the same opcode. And if you think about it, the shift amount value down here is really in the same field as the immediate value is over here. You can see that, all right? They just treat these most significant bits a little bit differently when they're shifting versus when they're anding and oring and so on up here, all right? I, though, still think of it as differently. We'll see more about that later on. Arguably, these R-type instructions are the simplest ones to decode and think about, right? I want to add 2 registers together, store the sum in a destination register. How do we encode that? Well, we have an opcode. All the R-types are in one group here. They all have the same opcode. We talked about the func3 last time, okay? We differentiate between what we're going to do by looking at the func3 code and, in some cases, the value of the func7 field over here, okay? What do we need to do to be able to express this instruction? So let's look at the add by clicking on add, and we'll get a much more detailed view of the same diagram, but now I've labeled all the fields and I put all the numbers in here to mark all of the bit positions where the fields start and end. And you'll see why in a minute. Again, I had to add this thing to the top of these diagrams the first time I decided I was going to write a disassembler for RISC-V. I needed to know all these numbers. And I kept on burning up lots of scratch paper, and then it dawned on me, I should just put what I like to call a cancellation on this diagram here so that everybody can skip the annoyance of having to count all these bits out by hand, all right? Okay, so what's going on here? The add instruction is described down here, as well as the and the or and the shift left logical and so on. A little narrative about how it works and the different examples and things like that. That's not really our concern right now. Remember, we're only focusing on the relationship between the machine language and the assembly language. We don't care what the instructions do in this for the sake of this current discussion, okay? We only care about if I say add and I give you 3 registers, how does that get encoded up here in this machine language? Or, put another way, if I give you a binary value or a hex value and I ask you to tell me what instruction this binary value is, you should be able to tell me. You look up the opcode. In the table on the last page, you find out that all the R-type instructions all have the same opcode. which is exactly this binary value here. And given that it is an R-type instruction, you can look at the func3 field, which is these 3 bits right here, and you can tell me which one of those instructions it is. And then you can continue over here to func7 and ask whether or not this bit is set in those cases when it does matter, like add versus subtract. Okay? So what does this thing represent? We should already be able to guess. The fact that this is on suggests that it's probably one of the shift or the add instruction. Okay, and I remember from before that when func3 is all zeros, that means that this R-type instruction is either an add or a subtract. If you forget, go back to the last page of the document and look it up. I just scrolled too far. Where are we at? Add and subtract have the R-type opcode, and func3 is set to zeros for both of these instructions. And when you subtract, there's a 1 over here in the func7, and there's a 0 over there in the add instruction. Okay? All right, back to this page. Now, how then would I print this out? All right, well, I can easily extract this RD value. And with all this labeling on here, it makes it real easy. This is 5 bits long. It starts in bit position 7, and it ends up in bit number 11. When you number these from the least significant bit on the right to the most significant bit on the left. So how would I then do this? Okay, well, if I got this opcode, I know that no matter what it is, it'll have an RD and an RS1 and an RS2 like this. And the thing over here, the mnemonic for this instruction, will be based on the func3 and the func7 over here, all right? So, okay, so far so good. I can make a lookup table, or I can put a switch statement or something like that in my code to do this sort of an operation. And I would need to extract this, right? Because this is the destination register number. If I wanted to express it, I would have to say X something, right? It would be X followed by the decimal value of this number here. So that's easy enough. I just AND this whole instruction with a value that's all zeros for all the bits over here and all the bits over there in order to kind of throw them away, leaving me with only the RD value here. And once I have that, I take this and I want to shift it to the right, so I got a decimal number between 0 and 31, which is what you get in 5 binary bits, okay? If you treat it as an unsigned value, of course. So what do you need to do? You AND it with a value, and then you shift it right 7 bits. That's why I put this cancellation up here for myself. I hope you find that useful as well. What if I want to know the func3 value as a binary, integer value? I do the same thing. I AND it with some value that has 1s in these bits and 0s everywhere else. In a C program, I can put 0B followed by 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and burn up my 0 key there. And 1, 1, 1 followed by a bunch more zeros for 32 bits total if I want. Or you can use these big slugs in here and do it in hex, which would be 0x, right, for hex, 0, 0, 0, 0. And then this hex digit would be a 7. 0, 0, 0 in hex. And then once I've ANDed this out of the instruction, I would shift that result right 12 bits, and I would then have an integer value that goes from 0 to 7 representing the func3 value. I could then use that in an if then else, else if kind of a thing, or another switch statement, or another lookup table, whatever I needed to do, okay? Same thing if I want to look over here at func7, I would AND all these ones out like this, shift it to the right 25 bits. What about RS2? And it with all ones in this range of bits, shift it right 20, and so on. Okay? That would allow you to write some simple little helper functions like get opcode, get RD, get func3, get RS1, get RS2, get func7, and so on. Get all that junk and all the shifting and the ANDing and the whatever out of your code to simplify everything. Anytime you have an instruction and you want to know what the func3 is, you could just simply write a simple little routine to get it out of there. So the R-types are pretty straightforward. I don't think we need to beat that dead horse too much. Let's look at the more complicated ones, all right? Let's start with the first one up here, these U-type instructions. They're both U-type, therefore they're both encoded the same way. They may not do the same thing. The source code might not look the same. Remember, we saw that with the I types. There's different ways to render an I type. Turns out the U types are both rendered exactly the same way. All right. So what's the relationship between this IMM field in the assembly language source code and whatever this thing is over here? Okay. You can click on IMM, Louis, or U type, which will take you up to, each one of them will end up coming up here somewhere in this range of the document, okay? So let's look at see how I decided to document this for you. Now, U-type instructions, there are only 2 of them, right? If you scroll down here, there's this diagram up here, and then there's the 2 instructions down here. If there were more, there would be more down here. Now we have the J-type, and you see a diagram of what's going on there and some other stuff. And you can see some of these get kind of nasty. So let's just take it one at a time and see what's going on. The U-type instructions, what these are for, as I mentioned last time, this is something you don't see on every CPU. What it really means is, look, ultimately it says take this immediate operand and store it in this register. Store it, we will see, in the left half of this register. Okay, at least, and everything I'm saying here applies to RV32I. It sort of applies to the other machine styles as well, but specifically I'm focusing on RV32I when I select my words. And what I'm getting at is, if this was an RV64I or an RV128I, this would work a little bit differently in those cases, all right? So take this with a little bit of grain of salt if you want to take my exact words and apply it to the other architectures. Again, I'm only focusing on RV32I right now. So what's going on then with this thing here? What does all this mean? All right, so this is a pretty straightforward one. These bits go straight down, and we just put zeros over here. So let's make sure we all understand exactly what I've drawn here. In an RV32I, the immediate value will be extracted from the instruction and converted as shown in this diagram, okay? So what do we got here? What is this an opcode of? You can look at this up on the last page. That's the Louis opcode. The Louis opcode only has one instruction for it. So if you see this one opcode right here, you don't need to look at anything else. That is the opcode for a Louis. It doesn't have a Func 3 and a Func 7 and other stuff you need to look at. This directly maps to the Louis instruction. And as we'll see, there's a single opcode as well for the AUI PC instruction. All right, those don't, again, they don't have a Func 3 or anything else that you need to consider. Okay, so this is a Louis. We know how to get RD out of here if we wanted to print this out given a binary number. You see this opcode, you just say, oh, that's a Louis. You see this RD value right here. What is that? That's 4 plus 1. That's the number 5. So that would be Louis X5 followed by something for this thing. Well, what is that? Okay. Well, that's what's weird about this one. The immediate value has 20 bits in it. And I put these letters in here so that if you can't follow the arrows so easily, you may not be able to figure out that A ends up here and so on. This one's easy. They all go straight down, okay? So the IMMU value that you see in the reference card in the second to last page of RValP here, the value that I discuss on that page, let's scroll back down and look, make sure we all know what we're talking about. Here's the Louis right here. And it says RDIMM. Well, here's what it does. Destination register equals the IMMU value. And advance the program counter to the next instruction. Okay? Again, I can click here and end up right where we were looking. Okay? Well, what's the relationship between IMMU, or more accurately, maybe down here, this thing here I mark and label as IMMU, and what goes in this instruction? This is called IMM. It is not called IMMU in this context, okay? So let's look again down here. What happens? Louis X23, 1, 2, 3, 4, 5, if that's in my source code, what does it mean? It means load register 23, because that's the RD register number up here, okay, with the value 1, 2, 3, 4, 5, 0, 0, 0. All right, this is not load register. This is load upper immediate, okay? So what it means is to take this number here, move it to the left, and store it in the destination register. How does that work? Well, it works like this. It takes these bits out of the instruction, it throws these away and replaces them with a 0. That's easy enough to do. It's take the instruction value and it with a hex F, 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 0, 0, 0. And whatever you end up with after that AND operation would look like this, would have all zeros down there. That result is what would be the IMMU, and that would be the thing stored in this register. Now, remember, I was trying to focus right now on just how to represent the relationship between the assembly language and the machine language, not necessarily on what the instructions will accomplish when they're executed. This one in particular, or more accurately, I should say, the U-type instructions in particular, we need to think a little bit about what it really ultimately does, because when we talk about an IMMU value, I'm referring to the value over here. When we're looking at a source code of an instruction and I say IMM, like I do with Louis over here, I'm talking about this value here, okay? Now, you kind of, in your head, need to realize that the Louis does this when it's running, okay? And when it's done, it doesn't shift this value over to the right. Like I've been saying, if you want to think about RD, you would AND this out and shift it over, okay? Same thing happens here, you just don't shift it, okay? That's how you read this diagram for the Louis. For the AUI PC, you literally do the same thing. AUI PC says, look, now this one doesn't just load a value ultimately into the register like we showed for Louis. Now that's the Louis instruction. What is this one doing? Well, ultimately, it's going to add this immediate value to the program counter. We don't care about that right now. What we care about is the relationship between this source code and this encoding up here. And it turns out the Louis and the AUI PC do the exact same thing. They look the same way. Notice that when I say Louis, I say destination register and this value. The value gets 3 zeros added to it when it's used, and when it's encoded up here. But in the source code, we just show the non-zero bits with the trailing stuff going on. AUI PC looks the same way in the source code. So if you said AUI PC, what do we got here? And I said 22 with this value here. All right, what it will do is it'll convert this value to the same thing that Louis does with 3 zeros after it before it uses it for anything. All right, and then we talk about down here how it gets added to what it gets added to and all this other stuff if you execute it, but we don't care. Right now, we don't care. What is the relationship between this source code line here and this encoding up here, right? And that's all it means, okay? So if I give you an instruction and you AND this thing out, you do need to shift it over to the right when you're going to print it. If you use, C out, double left arrow and then print out a hex value, you don't print these 3 zeros over here, okay? That's the whole point of this digression with the Louis and the AUI PC, these U-type instructions up here, okay? Now, in this section of instructions up here, I didn't draw all the extra lines. I kind of ran out of room on this page to put all these in separate boxes. But if you look closely, if it doesn't have a func3, each one of these opcodes is unique. Up here, this is the only time that happens, up for the U-type and the J-type up here, all right? This particular I-type is another standalone one that only has one opcode directly maps to jailer. Why? Because the func3 value is all zeros and there are no other ones that have this opcode, all right? So we just talked about the top two. Jail has this funky PC-rel21. We'll talk about that later. Jail R has obviously a base displaced addressing mode over here. Okay, so it turns out there's a lot of I-type instructions in here. All right, R-type we've discussed. We've discussed U-type. That's like 25% of the entire machine done already. We do the I-type, that'll leave us with well over half. So let's look at these I-type instructions. Regardless of which kind of I-type instruction, you have the same encoding. Now look at this one. This one doesn't simply say, take these bits and move them straight down here. In other words, throw this away and then use it. What this one does is it says throw these things away, shift this whole thing over to the right. So that's what I've drawn here, the massive shifting, right? And again, the letters help you when the lines get too close together. A, B, C, D, E, F, G, H, I, J, K, L right here get shifted over to here, A, B, C, D, E, F, G, H, I, L, all right? Now, we don't put zeros in here like I showed up here. What was it, with the Louis up here in the diagram with the, where is it? Here it is. See this one here? I just simply said, yeah, put zeros in here, all right? Instead, what the I-type does is it does a sign extension. We've talked about that before. It replicates this bit here. That's why I put a little box around it like this to say this bit means something different than the rest of these. It still has the same role. It's part of the immediate value, but this box around it means that is the sign bit in this particular encoding. And because we sign extend this, we end up with that A bit, whatever the value of A is replicated all the way in here. We talked about sign extension before. So when you shift this to the right, if you're going to write this in a C program, you could AND this out of the instruction, throwing all these away, making these all zeros. Or actually, you don't need to AND it at all, right? If I shift this thing right 20 bits, I've effectively thrown this away regardless of what it is. Okay? Provided that when I shift that value, the compiler treats this and does an arithmetic right shift by 20 bits, this value over here will be sign extended by the machine itself. All right. Now, as I mentioned before, using that technique is not always portable. The C and C++ languages don't specifically state that a right shift of a signed value will be sign extended and a right shift of an unsigned instruction will not be, and so on. So what I would do in this case is I would shift it to the right. And then after it's been shifted to the right, I would ask, is this bit a 1 or a 0? And if it's a 1, I'll just simply OR a bunch of 1s in over here. Otherwise, I'll AND it out and turn them all to zeros. That way it's portable. All right? I don't have to care whether the compiler does it or not. I happen to know that every compiler I've ever used, and I've been writing code for 40 years, works this way. I'm sure there's some out there that don't, and it's probably dependent on the kind of CPU that the compiler targets. So even the same compiler may do different things depending on the machine it runs on. You know, at times you would like to write portable code if it's easy and simple and obvious to do so. Just put it in your code is my point. If it's not and it's super convoluted, you can certainly document it as a bug or a design flaw or at least a warning. It says, by the way, this may not be portable code the way it has been written, all right? So if you do that sort of thing, at least disclose, all right? So that the poor person that comes along your code 8 years from now doesn't have to suffer through trying to figure out why it doesn't work for them. All right, so this is how you extract the immediate value for all I-type instructions, and I refer to this operation and the result from it as the IMM_I down here, all right? These are just my own conventions for this document so that we can have conversations and know what we're talking about. If I say IMMI, I'm talking about this thing here. If I'm talking about IMM, some other thing, here's another one up that doesn't have one, but here's an IMMJ, for example. It's extracted and shifted differently, okay? Let's still focus on the I. All right? Again, each one of these I've named. So what about the difference between the IMMI and the shift immediate? So I also say, oh, there's a special case for what I call shift amount I, okay? Now, it looks like this. Now, let's look very closely at the similarity here. This is why I think RISC-V officially considers these the same, in spite of the fact that I do not, okay? If you shift this whole thing over to the right and you sign extend it like this, and you use this in a shift instruction, ultimately the shift operation only uses these bits right here, H, I, J, K, and L, as I've drawn them here. Look at this diagram down here. H, I, J, K, L get moved down here. And all the rest of these bits I set to 0. So that's the same exact thing as creating this, followed by just setting all these to 0. Or you might say, as I do in my reference card, you could take whatever this is, no matter what all these bits are over here, and just say modulo 32 or mod xlen, and that'll give you this value here. It's the same thing. It's just ANDing out these bottom 5 bits, okay? So that's what this diagram down here shows. Just for the sake of completeness. I mean, if you actually built this actual hardware to shift versus add and whatever else you do with the IMMI up here, you literally would have to build a circuit that takes these 5 bits and throws the other ones away in order to get this value and then sends it over to the shifting hardware. Okay? So, all I-type instructions look the same. They have this immediate field over here. Shifting only uses 5 bits. The rest use all of them. The shift also has this bit hiding up over here. And sort of like as if it were treating these bits on the left as kind of like a Func 7 field. All right? When this bit is on and you're shifting to right on a RISC-V CPU, it's doing an arithmetic shift. If this bit here is a 0, when you're doing a shift right, then you're doing a logical shift right. I hope I've beat that dead horse enough so we all remember if it ever shows up on a quiz someday. All right, so there's all your IMMIs done. They all work the same way. That's how you get the values out of there. That leaves us with the S-types, the B-types, and the J up here. And I suppose the jailer down here as well. But the jailer is another I-type, and the discussion, you'll see that works the same way as the way the immediates do down here as well. So in relative ease, I suppose this might be the next easy one to deal with. All right? So far, what have we done? We've just extracted these fields and shifted them to where they needed to be. We had to do a special case with the immediates because we have to sign extend these. All right? In the I-types. What do the S-types look like? Well, closer look at an S-type. We got an opcode. We got a Func 3. We got RS1, RS2. And the immediate value is strewn over 2 different places. Now, why do you suppose that is? Remember what I said last time. Whenever a decision had to be made to make it easier for a programmer or make it cost less to use, own, and operate, and design, and manufacture, they choose the manufacturing, designing, the cost of ownership and all that. All right? So what does that have to do with this? All right? Well, look what's going on here. S-type instructions, these are used for storing values into memory. They don't have an RD value. Let's go back to the last page again. Look what's happening here. If an instruction has an RD value, it's always in this column. All right? Well, remember back when we were talking about how you actually design a CPU. Somewhere, somehow, something has to control your demultiplexer in your register file and tell it which register to store a result in that's coming out of an ALU or from the memory or something like that. It would be a nightmare to have to deal with getting the value. In this case, RD is that value. These 5 bits are what would drive the demultiplexer that routes to those right bits in the register file to say, I want to store something in this register versus another one. No matter what instruction it is, if it stores a result in a register, that RD value will be in these bits. There's nowhere else for it to come from. That makes your job much easier if you're designing the machine, because you just simply hook up these 5 bits from bit 7 through 11, and those instructions that use it, you're done. Those instructions that don't use it don't matter because they're not going to clock the write enable line to store anything in the register. And this is where we get to why the immediates are as screwy as they are. All right? That'll come back in a minute. And this will come back when we start talking about the B-type immediates and the J-type immediates in a second. All right? So, what's the takeaway here? No matter what, the opcode is always in bits 0 through 6. The Func 3, if there is one, is always in bits 12 through 14 right here. The RD, if there is one, is always in bits 7 through 11. The RS1, if there is one, is always in bits 15 through 19. RS2, if there is one, is always in bits 20 through 24. Okay? And again, these all get connected directly to various multiplexers and demultiplexers that have to do with choosing which registers you're going to be reading and sending to the ALU and which register you're going to write to. All right, it simplifies the hardware. All right, now we were on the S type. Why? Well, because the rule says if there is an RS1 and or an RS2 and a Func3, it must be here and only here. Whatever bits remain can be used then for an immediate value. Well, those are these bits here and here. So what do? Well, we take these bits out and shift them right 7 places, right? The little 7 there. We take these bits out. How do we do that? We AND them out, right? And we shift it right, not 25. If we moved it right 25, then the G bit would end up way over here, okay? So how far do I want to shift this one to the right? Look at how I've labeled this thing. Remember, I wrote this for myself when I was trying to write a disassembler. If I shift this field after I, and extract it, I shift it to the right 25 minus 5 places. That's how much it goes to the right. You do your math in your head, sure, 25 minus 5 is 20. If you take this bit here in column 25 and shift it right 20 times, it will end up in column 5, all right? But what if I want to shift this column here over to this one here? You got 15 minus 7. Okay, great, that's 8. But you do all this crud in your head, especially if you're fatigued and you're debugging your code. You don't necessarily notice maybe you added wrong. You could screw it up. This diagram, you can't screw it up. Don't do the math in your head. Even if you shift this one to the right, 7 bits, you could express that as 7 minus 0. Shift this one to the right, 25 minus 5, and so on. Then you can't go wrong. Let the compiler do the math that, it's always the simple things that when you're writing a program that you screw up. Anyway, my point is that's how you use these, what I like to call the cancellation tops of these diagrams here and all the little numbers in there. Again, this guy's got a box around it. Therefore, we need to sign extend the results over here. Okay? So this is how we extract the IMMS value. How do you use it? You just take that IMM value that you created, that you extracted by combining these things, and you express it in the instruction when you print it out or you think about it or whatever. Why else are we extracting this other than to understand what the instruction means? Well, I think of it in terms of its assembly language notation, right? So that's a store byte. RS2 is easy. You just grab it out of here. RS1 is easy. You grab it out of here. Again, X something. And the IMM value is just the decimal value of this signed value that you've extracted and shifted and sign extended out of here. Done. So that covers us all the way up to here, right? We got all the R's, the I's, the S's, and that leaves us with the tough ones, the B's and the J's. Let's look at the B-type instructions. What's going on with here? Branching. PCREL13. There's a lot going on here, okay? All the branch instructions, again, have the same opcode. We have a Func3 that differentiates between the different branch codes, the mnemonics. Right now, we're just trying to understand how to figure out what this thing means in terms of the assembly language, so we don't have to currently care what these actually do. We just need to know which one it's going to be based on the opcode and the Func3 value. All right? RS1, RS2 extraction, no problem. PCREL13, what's that all up to? And why does this IMM, what's the bar and all that stuff in here? Okay, let's go to the B type and get a closer view on what's going on here. There's 2 things at play here. There's a relationship between the IMMB value and the PCREL value that gets printed down here in the source code. Let's start with the IMMB value first. We'll see what's going on with this guy. It's twisted all over the place. Before I mentioned that you can never have an instruction in an odd address, okay, in any version of RV, any RISC-V architecture, okay? So because that's true, and because there's only so many bits in an instruction, and remember, these are branch instructions, And what we're going to see is these are base displaced addresses. It would be nice to be able to branch as far as we can given the number of bits that we have in the instruction here. Now, as I mentioned before, they had the foresight to understand that someday they would want to have what we call compressed instructions in this system. And they decided that, in theory, an instruction could be expressed as a half word, a 16-bit value. Therefore, it is legal to branch to an address that's a multiple of 2. Okay? So, in a multiple of 2, we know it's an even number, therefore the LSB is always a 0. Therefore, you don't have to waste one of the bits up here, is my point. Expressing this 0. It's always 0. So forget it. Take your immediate value and use it to express an integer value, a displacement, a signed displacement at that, right? This is a signed bit up here. Therefore, you can branch with a negative displacement and a positive displacement using these functions, forward and backwards, okay? To any legal address, right? Now, RV32I does not have compressed instructions. Therefore, this X over here, for us, will also always be 0, because all those instructions must be on a multiple of 4 boundary. Any binary number that ends with 2 bits of zeros is a multiple of the place value of this column here, just like if this was in base 10. Any base 10 numbers that ends in double zeros is a multiple of 100, right? Well, any binary number that ends in with 2 zeros is a multiple of whatever this column represents, which is 4, okay? So all 4-byte instructions will always have double zeros over here. So this is a little bit wasteful to encode them this way with RV32I. However, the designers of the RISC-V architecture decided that it was going to be so common to include compressed instructions that it's okay to be a little bit wasteful in the one unique case, like the one we're focusing right now, on only integer instructions. We can waste that 1 bit in this one simplistic case, all right? So that's why this is the way it is, all right? So what about all this crisscrossing in here? We'll see more about that in a minute. The takeaway right now is kind of like, who cares, really? These bits here need to be shifted. You know, you extract them and shift them to where they belong. It's as simple as that. Just put them where they belong. You know how to do that. And it, shift it over, right? Well, what's this one? Well, if this is bit column 7, this is number 8. This needs to be moved to the right 8 minus 1 bits in order to get this X here to end up in this column over there. This bit here, you know how to extract 1 bit and then now I need to shift it the other way. Well, that would be 11 minus 7 because you're going the other way. 4 bits to the left, right? It would be, what is it? Straight down, would put it like right here. 1, 2, 3, 4, right? No brainer. Same thing still works. What about this stuff way over on the left? Same thing. And it out, shift it right, whatever 25 minus 5 is. Okay? Now notice they're in 2 groups. We would want to extract this. Shift it right, 25 minus 5. Okay? Then extract this 1A bit here. And shift it right, 31 minus 12. To put it here. And then we would OR in all these as 1s if A up here was set to a 1 to replicate it, to sign extend it all the way to the left. Okay? So, why like this? Well, it's because of this 0 over here. Remember, save money at all costs, right? We're going to try and save money on the machine. Well, remember this other encoding down here that we already looked at. See this one down here? This is the S-type instructions. In the immediate up here, look what's going on with the B-type. See what it has, like 12 and then 10 through 5. And then we have 4 through 1 and then 11. That's what this notation means here. And that's exemplified by all the arrows we were just looking at above. And then down here we got what the 4 through. Let's just focus on this column right here for a minute. IMM bits number 43210. This is a range. Okay, the least significant 5 bits is what this says. 0, 1, 2, 3, 4. There's 5 bits in this field, and they end up going into bits 0 through 4 when you're using it as an address for the store instructions. Okay, up here we got 4 through 1. Those bits 4 through 1 are in the same place as 4 through 1 in this guy down here. What's not in the same place is this 11 out here in the middle of nowhere. Okay, but 4 out of 5 ain't bad. Again, how much circuitry do you think it's going to take if you just move all these over and say, oh, I want to make this organized? You're going to have to pay to have all these bits rearranged in multiple ways. If 4 through 1 can be stored here, and it's the same place that 4 through 1 are stored in this instruction down here, well, then we'll do that. Okay? Why not? Okay, that leaves 11 as a special case. And look what we got going on over here. And up, where's the other one? Up here, right? So we got 10 through 5, and then 11 goes there, and number 12 goes over there. So what we have now, and think about it in your head, right? If 11, 10, 9, 8, in that order, it's arranged from 11 all the way down to 0, and all in order in this field here. Well, at least bits 10 through 5 in a B-type instruction are in the exact same place that bits 10 through 5 are in this I-type down here. So just like making the argument about the relationship between the bits 4 through 1 are in the same place, we're going to see that bits 10 through 5 are also in the same place as this I-type instruction over here. Okay? Now, this instruction ends with bit 11 on the far left. They could have put bit 11 on the far left here if they wanted to, but there's another reason they played this extra game over here. So let's go ahead and look back up here at the B type, and let's look what's going on here. We played a little bit of a game with the number 11. And 12 is sitting over here on its own. Notice that every single instruction that has an immediate value has the sign bit in the same place. It is always in bit 31. If it has a sign bit, it will be in bit 31. Now, why is that useful? Well, it's useful because if you have an instruction with an immediate value that needs to be sign extended, you could build a circuit that does the sign extending. And the only thing that circuit needs to do is be told what the value is in bit number 31. It's not some instructions have the sign bit here and other ones might have it over there. It doesn't matter. It's always going to be in the far left position. Okay? Now think of what I said about bits 10 through 5 and the 11 and so on. Well, in this branch instruction, unlike the I-type instructions, this thing has a bit number 12. The other ones have a bit number 11 is the most significant bit. Well, if the most significant bit is the sign bit, then by definition, this bit over here must then be bit number 12. It can't be bit number 11. That's why we've got 10 through 5 in here, but not the 11. It's more important in terms of money in designing circuitry that this always be the sign bit, in other words, than it is to simply say it's always the most significant, it's always going to be bit 11 or something like that, right? So if we scroll up to the I one up here, it's the S type. Where's Mr. I? Here's the shift one. Here it is. So this one was nice and clean, but the sign bit here happens to be bit number 11. All right? So when the sign bit happens to be bit 12, we got to get bit 12 over there on the left is the point, okay? So that leaves us with bit 11 going in the place where this one does not have a bit 0. The immediate value always has a 0 down here, so they don't even store it. Why bother? We already talked about that. So that leaves us with one weirdo is number 11. Well, stick it in the one bit that doesn't get used, and it's a single bit. It's a single wire inside of the CPU that we have to deal with in a special way. Everything else is standardized. If you got bits 1, 2, 3, 4, and 5, 6, 7, 8, 9, 10, they're all going to come from the same place. So let's save money on all these and waste money on only these two. I think that's a good choice, right? Rather than wasting money on all of them. Okay. So that's how you extract the value from the B-type instructions. Now let's go look at the PC-REL 13, and this is going to be related to PC-REL 21 as well. And once we've done this, we've covered all the bases. Let's look at PC-REL 13. You click on that, it takes you up here. Well, a nice detailed definition, right? An address that is within minus 4K to plus, 4K minus 1 of the current instruction location. These addresses are typically expressed in assembly code by using a label, RISC section blah, 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 for examples. Oh, that should be the thing we were just looking at. Here's the diagram we were just looking at down here, but we scroll up. Let's look and see what these instructions look like in the source code now. All right, we're all kind of accustomed to the idea that, it would be nice to have the programmer be able to write programs in a domain that they understand. Otherwise, we'll just be typing in these hex values all the time, right? So let's say I have an instruction sitting in my program, and I want to branch to address 0. Well, this is an instruction stored at address 0. This is an endless loop. Okay? What this means really is branch if these two registers have an equal value in them to this address over here, hex address 0. So if they happen to be equal, this is an endless loop. But that's beside the point. Let's look and see how this thing is encoded and what it means. What is this? This is the target address of the branch instruction. Look what's going on down here. I've got branch if equal, again, now I'm going to say branch to address C. It could be a label. It could just be a hard-coded address number in my source code. Okay? Here's the same instruction again, branch of equal, yada, 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 to address 0. You might think that this instruction here and this one up here are encoded exactly the same way, but you would be wrong. Look at this, 00520063 for this instruction up here. What about the one down here? FE, blah, blah, blah. Very different, okay? This gets us into this PC relative jazz. That's why this is called PC-REL. And the value over here is the immediate value for branching, or IMMB down here, okay? So how do we relate all these? Let's look and see what's going on down here. Now, this narrative down here goes along with the discussion up here because it floated the figure to this page when I formatted this document. I'm sorry about that, but let's see what's going on here. Instruction at address 0 is a target address 0, and an IMMB is 0 because the offset from the current instruction to the target address is 0. And I got a little footnote in here. This is in contrast to other instruction sets like the 68K or the Pentium and the AMD chips and all that other stuff. These are called program counter relative addresses. What's happening here is we'll see the base register in this calculation is the program counter. Okay. The most machines use the value from the program counter that is the address of the next instruction. So in this case, if it was another machine, what this would do if I wanted to branch to address 0 from an instruction at address 0, and if that instruction consumed 4 bytes, this IMMB value inside this instruction would be set to -4 because the program counter that is used in a calculation in those other processors would be this 4. Okay? In the RISC-V, program counter relative addresses are expressed based on the address of the current instruction that is executing within which the address is used, okay? So in this case, we'll see all these 4 zeros hiding in here comprise most of that IMMB value, and you would say branch to, you would think of this, I think of it in my head as 0 off of the program counter, okay? And again, RISC-V uses, the program counter is always pointing to the current instruction until it's done, rather than advancing to the next instruction right away while the current instruction is executing, like a lot of other systems do, okay? Okay, so with that in mind, what do we got here? At address 0, we're branching something or other to address 0. At address 4, we're branching if something is true to address C, and so on. So when you look at the narrative down here, what is it saying? The instruction at address 4 is a target address of C. That's the middle one of these three. Okay, that's this one right here. And the IMMB value is therefore 8 because the current address in the program counter is 4, or I could say the address of the current instruction is 4, plus that IMMB value of 8 equals then the C, which is the target address for that branch. So when I say PC rel 13 in the usage statement for one of these branch instructions, what I'm talking about is an address whose value can be expressed using an IMMB value that can be added to the address of the current instruction. In other words, this is a 13-bit number at most. It's signed, okay? All the immediates in RISC-V are signed, and they sign extended, right? So within 4K plus or minus of the current instruction. This is incredibly useful. You don't need a base register all the time like you do on a mainframe. Mainframes don't have program counter relative addressing, at least not in BC mode or EC mode. RISC-V definitely does. All the conditional branches in RISC-V use program counter relative addressing. And the way they're expressed in the usage template here is you put the actual address that you want the program to branch to in here. And when the assembler runs, it takes that actual address and subtracts off the address of the instruction itself to calculate what will be IMMB, and it stores it encoded in this weird unrolled and folded up way in the instruction, all right? So that's, again, if you look closely inside this instruction in here, in order to get to address C in hex from this instruction, when this condition is true, it needs that there has to be an 8 hiding in here somewhere. All right? So let's look at what this is. You get 00520463. Now, I think we can sort of see what's going on without even looking at all the unwinding down here in this diagram, okay? Here's a branch from address 0 to address 0. We know in our head that the IMMB value in this instruction, wherever it is in here, must be 0. Just like we know that the IMMB value in this instruction down here has to be C minus 4, which is 8. So there has to be an 8 hiding in here. Look at the difference between these two encodings. Same. 0 here changes to a 4. And then same. The single bit that comprises this hexadecimal 4 is the thing that represents the 8 in the IMMB value. All right, let's look and see what's going on here, right? So we got, it's just all blah, 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 and then we got a 463 over there, right? Well, the 63 is this opcode and this Y bit right here. Well, we know Y has to be 0, because otherwise this value can't be 6, right? 0110 is 6, and 0111 is a 3. So the 63 says that shall be 0, followed by this stuff over here. Now, what was in this hex digit over there? That's that 4, right? Oops, I scrolled too far. That's this 4 right here. Okay? Third hex digit over is the 4. Well, that's these bits right here. Well, what's a 4 in binary? Well, there's a 0 and a 0. That's a 1 here and a 0 there. All right? Now, when this is extracted and shifted to where it belongs, the V bit here ends up right here. Well, remember this IMMB value has to end up having the value of 8, right? Well, if V is a 1 and every other bit that comprises all these other letters are all zeros, then that means this is a 0, 0, 1. That gives me my 8. And all these others have to be 0 as well, right? Well, we already know the Y is a 0. So we know that one's a 0. And we know that all these are zeros because, when you look at the encoding up here, you see these two zeros on the left. Well, those coincide with all these bits over here. And all the other bits in the instruction have to do with the source registers and the func3 and the opcode, right? So clearly, this thing here is an IMMB value of 8. This thing down here, look at all F, E, and all this other junk going on. I'm at address 8. I want to branch on some condition to address 0. Well, I know I have to go 8 before me to get to 0. So all the bits hiding in here must be negative 8. I'll leave that as a task to a viewer to map all these hex digits out. The short of it is, remember, the most significant bit is always the sign bit in the instruction. It's always this A bit down here, no matter what the encoding is. And because this is an F, we know all 4 bits here are 1s. Therefore, we know all of these are 1s, right? A, B, C, D, which means this is a negative number. Okay? It's not a big negative number because for all these to be 1s, then you only have these that could be non-zeros. It's nearish 0. We know it's supposed to be negative 8. Look at the rest of the bits in here that are hiding in this 0, C, E over here, and you'll see that this thing comes out to a negative 8. All right? And that's the relationship between the PC-REL13 and the way we encode it to create our IMMB. All right? That leaves us with only one left. That's this J-type right here. The biggest, messiest one of all. If you look closely at the bits in here, what do we know about it? Well, the most significant bit of the IMM value is, again, on the left. And it's a 20-bit value, right? 1, 2, 3, 4, 5 hex digits. Each of us is 4 bits. Therefore, it's a 20-bit value. How come that's not 19 then? It's because there's no 0 in here. Remember, just like the branch, the jump instructions always have a 0 in the least significant bit, so they don't bother to store that. So it's a 20-bit value in the instruction, but it represents 21 bits of the IMM J value that we're going to see in a second here, right? So this mess up here is going to be unfolded and unwound. Let's look at some of these bits for a minute. Bit 20 is the most significant bit, therefore it must be furthest on the left. Then you have bits 10 through 1 in here. Well, look what's going on with that. These bits 10 through 1 are in the exact same place as bits 10 through 1 are in this instruction over here. All the I types have bits 1 through 10. All but 2 of the bits in this immediate value of an I type instruction are in the same place as they are in the J type. So that gives us 10 bits, again, that we don't have to find somewhere else to store them. These bits 19 down to 12 turn out to be in the same exact place as they are in this instruction up here. All right? If this is 12, 13, 14, 15, 16, 17, 18, 19, and so on in there, that turns out it's the same place as they are in this guy up here in the U type. All right? So that makes only bit 11 and 20 different in any way from any other instruction. 2 out of 20 is a good cost savings. All right? That's why it's folded around and twisted like this. Again, just like the B type. Most of these bits turn out to be in the same places as other instructions. Same thing with the J type. All right, so a PC-REL21 can represent plus or minus megabyte. All right, down here, here's how we do this one. Now we've got a couple of twisted and stuff. These guys come straight down. Why? Because those are the ones that came straight down in the U-type instructions. These guys on the left get folded around and shifted over to the right, just like they do with the I-type instructions, all right? Leaving us with a couple of weird cases, all right? Well, it doesn't have a bit 0, therefore, what was bit 0 in the IMMI type instruction is recycled to deal with this bit over here that had otherwise nothing to represent it, okay? And the other one that's unique is the most significant bit over here. So that's used for the most significant bit of my result and the sign extension, just like all the other IMM values, all right? That's why these things are twisted like this, all right? Bottom line, there's a reason. If it's not obvious, it means you just didn't think about it hard enough, okay? Again, only even addresses on a on all RISC-Vs. On a RV32I without the C extension, we talked about the extensions before, this K bit will always be 0 as well, all right? So I'm only a little bit wasteful, but a lot of reuse when you think about all the wires and the gates and the multiplexers and all that fun stuff. Okay, so here's it's only used for this one single instruction, which is JAL, and you got an RD register and this PCREL 21 value here, okay? Now, just like the branch, this is program counter relative. So when you write your source code, you take this value here and you subtract off the address of the instruction that is being assembled in order to come up with the actual IMMJ value. Again, these are signed, okay? So you can end up with a branch forward or backwards, okay? And a little narrative in here talks about ultimately what you're going to do. The same kind of a thing we talked about with the branch instructions. I'll leave that as a test for the viewer to work this one out using these example addresses and these example instruction addresses. All right, so that's how the encoding and decoding of all these instructions works on a RISC-V. Thanks for watching. See you next time.